Hey, welcome to Complex Numbers Part 6. Hey, what's it called? Polar form to the rescue here. Polar form to the rescue. Why do we need to be rescued? Well, have a look at this up here. 1 plus 3i to the fourth would be that sort of expansion. Would you really want to do that? Completing several foils, first, outers, inners, last, and all that? Or what about this one? Oh no, not that. 2 take 5i to the 8th times itself 8 times. Well, what's the quickest way we could do it if we stayed in that form? Well, we could use this, NCR, CNR, sometimes written like this or like this, and the combination of n brackets take an r at a time, and it's the first term to n take r and the second term to the r, the binomial formula, isn't it? We could do that rather than just expand all the brackets, but that is what? Painful, terribly painful. Now, you might already know about r cis theta form, or the polar form, and so you would probably have a good idea. It's going to be easier. So let's have a look at why it is easier, and here's a little example for you. So if z equals x plus yi is in r cis theta form, polar form, then z to the fourth would be this, and it would be r cis theta to the fourth, which would look like this here. And we know these are all real numbers. Okay, the modulus of a complex number, modulus of z, which we're calling r here. So it would be r to the fourth. And from the properties of cis that we've established in an earlier presentation, cis theta by cis theta by cis theta, you add the arguments. So it's cis 4 theta. So then we could, if we wanted to, bring that back to x plus yi form, if we wanted to at the end there. Okay. So, and that's usually the convention, by the way. If you're given something like this up here as a power of a Cartesian form, then the convention is that you will return to the same form as the problem was given initially. But gee, isn't that nice? That's an easy way of multiplying complex numbers, and therefore also of raising any complex number to a power. So we've been saved by polar form. Let's have a look at de Moivre's theorem, sometimes called de Moivre's theorem, but let's just come down here. But he was a Frenchman, de Moivre, so probably saying it that way might be better. Here we go. What did he say? Well, the r is the modulus of z, isn't it? Cis theta all to the n is the r to the n cis n theta. Okay, so that's what we've just been doing with the fourth power. Can we sort of generalise that a bit? And let's have a look here. So for any positive integer n, and some screen clippings this time coming from Hayes and Harris publications. So you're going to do this. What does it mean? Well, it means n lots of these all laid out. Here we are, n lots of mod z cis theta, or r cis theta. So you can put all the mod z's out the front. There's n mod z's there, and then all the thetas, n thetas, and from the properties of cis what we established before, you multiply, moduli, add arguments, so it's going to be cis n theta. You might look at a process of induction to prove that theorem also. Okay, so there we go. That's the idea. Now, what could n be? We're thinking of n as a what? A positive integer here, aren't we? Overall. Could it be negative? Could it be a fraction? A rational number? Fraction of ratio of integers? Let's go down and play a bit down here and have a look. Here's the first case. If you had a negative in here, you could think of this as 0 take neg theta, and subtraction here, subtraction of the angle represents division in cis, so cis naught over cis n theta. And here's the rule here, the cis rule, if you like, from the rules of cis. Cis of theta divided by cis of phi is cis of theta take phi. You subtract the arguments. That was established earlier as well. So here, therefore, if cis of naught is 1, here we've got it here, then this is 1 over cis n theta. And you could call that then, from the properties of cis again, that's 1 over cis theta to the n, right? N lots of theta. We've just talked about that, where n is a positive integer. So this comes to cis theta to the neg n. Oh, so it does mean that you can use the theorem for negative values. Let's connect these two up. Okay, cis theta to the neg n is cis neg n theta, which is the negative equivalent to our de Moivre's theorem from above. Okay, there we have it. So now we can have a negative integer. What about n being rational or a fraction? Let's just check that now. So here's a little proof. So what we're going to look at here is rational n. Now rational is ratio now. So that implies it's a ratio of integers. That is a fraction type deal. A ratio of integers, a fraction. So let's have a look at a little proof here, or a little investigation. Cis of theta on n to the n, we would say is, let's apply the rule, n times theta on n, which is cis theta. Okay, so that's where n is a positive or negative integer here. And so if you were going backwards here, cis theta to the 1 on n, what you would do is that would cancel out that, wouldn't it? Let's have a look at that. Cis of theta on n to the 1 on n equals cis theta. So if you want to raise this to the 1 on n, oops, so that's to the n. Okay, so here if you want to raise this to the 1 on n, you have to raise this to the 1 on n, and it comes to cis theta on n. So because of this relationship here, that coming to cis theta, going backwards, cis theta to the 1 on n comes to cis of theta on n. So it's also true now for rational n. Okay, so we can apply it there as well. The set of integers and also rational n. So the set of integers are positive and negative, we just established that. Plus some fractions can be put in there as well. All right, interesting little manoeuvres, aren't they, with these rules of cis? Okay, so here it is. There's our result. This time we've enlarged it to all rational n. Okay, so that covers integers. Integers are rationals, aren't they? They're rational numbers because an integer like neg 3 is written as a ratio of integers as neg 3 over 1. So just remember that name there, rational, ratio of integers. So that covers all the positive and negative integers and the fractions there. All right, do you want to use it? Let's see what we can do. One of those on the opening page looked pretty bad. Here it was, this thing here, root 3 plus I, that type of thing, to the 8th. To the 8th. So let's convert it to our cis theta form. Remember, with multiplication of complex numbers and division, but certainly powers as an extended form of multiplication, the cis form, our cis theta form, the polar form, is a big help. So let's find the modulus of this one, which is our value. So it's the root of real part squared plus imaginary part squared, root 4, which is 2. So now we can divide through, divide root 3 plus I by 2, and we get 2 by cos theta plus I sine theta. Or on your diagram, arctan theta, here arctan, of 1 on root 3 to get theta, and that angle of course is pi on 6 if you know that. Now, you can do it either way using a tangent. If you use the tangent, but just make sure which quadrant you're in to be sure there. Okay, so that's pi on 6, so our cis theta form for root 3 plus I is 2 cis pi on 6. Okay, so what are we going to do now? Let's have a look at raising it to the 8th power. Here it is. Here it is. We're going to go with de Moivre's theorem, 2 to the 8, cis 8 pi on 6. Right, so here, that to the n, mod z to the n, and n theta in here. So we get down to 2 to the 8 cis 4 pi on 3. So we could do that. Let's have a look at it on the diagram here. 4 pi on 3 is right around there. And this would be 2 to the 8th out there, that length of that line. But if we were plotting it on an Argand diagram, they're just showing us the angle here. Okay, to get the idea of now what we want to do is to come back to x plus y or Cartesian form. Okay, so here we are. If we work these out, cos theta, cos is going to be negative and equivalent to the angle pi on 3 in the first quadrant, right? And then cos of 4 pi on 3 is going to be equal to the negative of, sine of 4 pi on 3, negative of the sine of pi on 3, which is root 3 on 2. Because cos theta plus I sine theta. So we can use our diagram here to show that we are going to work with an equivalent angle in the first quadrant. So that would be pi on 3. And these would be the negatives. So those triangles are congruent. And we know up here this is cos pi on 3, sine pi on 3. We use that from our trig or circular functions work. Right, you could do it on the calculator, of course, and go, if you did it on the Casio, go into run mode and then complex so that it can pick up I and then raise it to the 8th. And it will give you this form here, and just noticing that neg 221.70 whatever is neg 128 root 3. So you can do that neg 128 root 3 and that's the number you would get. Alright, so are you ready to do all that? Remember, polar form to the rescue here. So let's have a look at 2f. And here are some problems for you, basically just on de Moivre's theorem. And I think you probably don't need to do all of them, probably alternate parts here. So question one where you start with R cis theta form. Question 2 where you actually have to convert the complex number from Cartesian form to polar form. Okay, so in 1, you start with polar form. In 2, you have to change the Cartesian form to polar form first. And you could do some answer checking with your calculator. Okay, so I'll leave you to look through those. There's some interesting ones there. So pause it, have a go. I'll show you the rest of the set and then the answers. Okay, so 5, 6, 7, 8 and 9, you might have a look at some of those. Certainly some of these trickier ones with the proof there. Think about that and how you would handle ones like that. Doing a division there, z squared take 1 over z squared plus 1. Just thinking about that. Okay, let's have a look at the work solutions now. Well, there's question 1 and part of question 2. I'll have a look through those. You must be able to do this. This is fairly basic work and crucial work. But there's the rest of question 2. Okay, let's go down to question 4. 4, 5 and 6. We'll come up to 7 in a minute. Okay. And question 7. Part of 8 there. Okay, there's all of 8. And 9, did you get that one? Important here to see that z squared is best done with cis form, and you go through and you can simplify that. Alright, how did you go with that? There's one little thing, one little trick we can do with this, apart from those two, so come down and have a look at it. Okay, here we are. This is an interesting one. Playing with cos 2 theta plus I sine 2 theta, or any other multiple of theta there you could do. Deduce the duplication formula. Okay, so can you pull it apart and get other expressions for cos 2 theta and sine 2 theta? All right, well, of course, starting with this, we can say that's cis 2 theta, and that's cis theta squared using de Moivre's theorem. Okay, so what that means is it's cos theta plus I sine theta squared, going back into a Cartesian form. And if you expand that and collect real parts, I squared sine squared theta, in the expansion of that is minus sine squared theta, so you've got the real part, the imaginary part is 2 sine theta cos theta. Okay, so what can you say? Well, the imaginary part, sine 2 theta, would be 2 sine theta cos theta. There it is there. And the real part, here it is going to be there. Okay, so interesting, isn't it? And you could do something similar, of course, for any multiple of theta. Cos 3 theta, or cis 3 theta, cis 4 theta, and use a similar approach. So it's an interesting trick, isn't it? Delving into complex numbers and coming out with a result on the duplication formula. That gives you an idea that when you're in complex number land, you don't necessarily have to stay there. You can use it to prove results and come back out with a interesting result in the real number set. Okay, come down and let's have a look at these. Oh, I've gone too far there, so just go up a bit. So you have a go at that without seeing the answers. Okay, so there it is there. Cos 3 theta, sine 3 theta there, trying to get relationships for those. And in 11, you must have a go at 11, because that's an interesting result. 1 on z to the n. Now you know the rules for that now, so you should be able to just apply de Moivre's to both of those, and away you go. Let's have a look at the answers, and we'll finish up there. Okay, so pretty much as you would expect, I think in question 10, were you able to get question 11? Some interesting little algebra down here, so you need to think about that. All right, there is one more presentation in complex numbers, and that's to do with equation solving, and there's some interesting surprises waiting for you there, I think. So it's cheers for now. I'll catch you in that one.